Okay, so we just left off with an exercise, which was just this defining feature of linear classifiers, that there is this separating hyperplane. On one side of the separating hyperplane, we're predicting as a 1. On the other side, we're predicting as a -1. And then I asked, what's the normal vector to this hyperplane? So this is really just a re-expression of what we of this classification rule to begin with. So hopefully you didn't overthink it. I just wanted you to play a little bit with these terms and think about what a hyperplane is. So first of all, a hyperplane, what is it? It's just an equation of the following form. It's any x that satisfies B transpose x is equal to A for some vector B. So let's let x prime and b prime just be the coordinates 1 to p. Remember, there's an intercept term, and I want to omit those, right? I want to think about everything other than the intercept term. Well, we know that the intercept term x0 is just 1. And so if we think about beta transpose xi, well, that's beta naught plus this beta prime transpose xi prime. Right? So I'm just isolating the components that don't correspond to the intercept term. And now this beta transpose xi equals to 0 is equivalent to the following thing, which is minus beta naught is equal to beta prime transpose xi prime. So this is a hyperplane, right? This is a hyperplane equation just like we have above. And to be on one side of the hyperplane means that minus beta naught is less than beta prime transpose xi prime, and greater than for the other side of the hyperplane. And the normal vector, we know that for hyperplanes of this form, B here is one of these normal vectors, and so the beta prime in this case is the normal vector to this hyperplane. So to answer this exercise, you just had to go back and remember what hyperplanes are and what their normal vectors are from undergrad. Okay, so we started off talking about what we want to do. We want to do this 0-1 loss minimization. We want to minimize our empirical risk under 0-1 loss. But we mentioned this is an NP-hard problem, and it's because of this discontinuity of the empirical risk in the beta parameter. And so one way that we can deal with this is to rewrite, and first of all, I'd like to mention this isn't always 0-1 loss. Minimizing 0-1 loss empirical risk is not always an NP-hard problem. One notable exception is an Ising model over networks. That actually turns out to be something that we can solve using graph cuts. So it's not always NP-hard, but in this case, it's not an easy problem. There's no easy solution for this case. So the way that we deal with this is we just rewrite this 0-1 loss in the following way, and then we think about how we can create surrogates to this loss, and we call this a surrogate loss. Right? So let's rewrite this 0-1 loss for this linear classifier. So the 0-1 loss here is based on beta and of course xi and yi, the data, and let's just write it as the indicator that yi times beta transpose xi is less than 0, right? And we can see that this is exactly the same as what we have above. So this is less than 0 if and only if these signs don't match, right? And so now the idea behind making this continuous and not discontinuous is that we think about this indicator function. This indicator function is very discontinuous and also non-convex. So let's think about changing this and coming up with some continuous versions, continuous surrogates for this loss. So one of them is called the logistic loss, and this is the loss that's used in logistic regression. We have the loss is the log of 1 plus the exponential of minus yi times beta transpose xi. So we just take this inner term in the 0-1 loss, and we just replace the indicator that it's negative with log 1 plus exp of minus that. Similarly, we could think about the hinge loss instead, and this is the positive part of 1 minus yi times beta transpose xi. There shouldn't be another parentheses here. And remember, the positive part is just the value if it's positive, and it's 0 if it's negative. So we'll look at these specifically, individually, and their properties. But they're supposed to be surrogates for the 0-1 loss. Okay, so we have these different classification loss functions. The 0-1 loss function, as a function of yi times beta transpose xi, it looks like the following. It's 1 for the negative values of this, and then it goes to 0 for positive values of this. And positive values of this mean that we've done a good job of prediction, right? Because our beta transpose xi, we're predicting with the sign of that. And so if the sign of that matches the sign of yi, because remember yi is 1 or minus 1, then this thing being positive means that we correctly classified, right? So this side is good, this side is bad, right? The positive side is good, correct classification. The negative side is bad. And these losses are nice because they are higher for misclassifications than they are for correct classifications. Now they have slightly different properties. They both asymptote to a line, and they both taper off towards 0 as we go, as this value approaches infinity. But the hinge loss is non-differentiable. It has this point, just like the absolute value function, where it's non-differentiable. It also, for some correct classifications, it's non-zero, just like the logistic loss. There are some correct classifications for which this is non-zero, right? So the loss isn't 0 for correct classifications, and that's where we really suffer a little bit. It might not be significant, but we suffer some based on this fact that we have some loss for correct classifications, which is sort of an undesirable property in some sense. But this really is unavoidable if we want the loss to be above a certain value for misclassifications. So for example, if we want all the losses to be above 1 for misclassifications, then you really can't have it jump to 0 without having a discontinuity. So the hinge loss, you can convince yourself, and I would encourage you, I didn't make this an exercise, but I would encourage you to go back and just convince yourself that these are the shapes for these two losses, specifically the hinge loss. Convince yourself, go back to the definition, that it looks like this. Just draw up these lines. Okay, so what does this look like in terms of the losses that we incur? So what I did is I took those same points, and this line is our separating hyperplane. On this side, we're going to predict as positive. On this side, we're going to predict as negative. But then let's think about the losses for the logistic loss. So as we get further into this positive part, the positives are getting smaller and smaller losses. That's because the yi times beta transpose xi is getting larger and larger, and they're inversely proportionate in this way. And so these losses are getting smaller and smaller as we go over here, but they're non-zero, right? Same with this negative part. The losses are getting smaller and smaller as we go away from the margin, but these are correct classifications, but they are getting smaller. If we look at the misclassifications, those are these red dots on this side. We predicted negative, but these are actually positive, and they do have larger losses. Right? So that's a nice thing about this, is that we have that property for the logistic loss. If we look at the hinge loss, this is sort of interesting. There's some point at which the losses just become 0, remember? And that's these misclassification, or the correct classifications over here, are all weighted 0. Right? And so we see that actually some of these are gone. And the hinge loss is used in support vector machines, and we consider these points here to be the support vectors. We'll talk a little bit more about the support vector interpretation of SVMs, but for now I like this surrogate loss interpretation. I think it's very well motivated, and it gives us a good comparison between logistic loss and hinge loss, one unified philosophy to talk about both simultaneously. So that's a property of this hinge loss, and it sort of induces a sparsity in these supporting vectors. Okay, so points weighted by the square by our square loss. So instead, suppose that we just used a square error loss, which just says that we would take yi minus beta transpose xi and took the square loss of this. We could rewrite this square loss as the following thing. So we have our yi minus beta transpose xi squared, and we could rewrite it as 1 minus yi times beta transpose xi squared, right? Because the yi is plus minus 1, so we can just multiply the inner part by yi squared, and we get this thing. So this is one way to express the square error loss. So it's also a function of this yi times beta transpose xi, just like the other losses. But it's this particular function, which is 1 minus yi times beta transpose xi squared. So let's look back at that picture. These blue points over here are correctly classified. These blue points over here are incorrectly classified. Right? And this line right here are the points at which xi transpose, beta transpose xi is equal to yi. Right? This line right here. So we have these high losses for points which were correctly classified. Not only correctly classified, but they're very far from the margin. So they're very correctly classified in some sense. But we still are incurring a loss. And this is the problem with the square error loss for classification, is that as a loss, it's giving these high losses to very correctly classified points, which probably is an undesirable property. You could imagine that that would push our loss to worry about these points, which we shouldn't be worrying about because they're correctly classified. Not just correctly classified, but they're very far from the margin. The same with the red. We have these points over here which have a high loss, but they're correctly classified. So that's the problem with the square error loss, and that sort of answers that first exercise we gave. So this is a comparison if we include that square error loss here. We see it has this nice property that it blows up in these incorrectly classified points. It gets small, but then it gets large again, which is why we don't like square error loss for classification. So we'll return in the next lecture, in the next video, with talking about ridge terms and the other more classical interpretations of ridge and logistic regression. I like to start off with a surrogate loss interpretation of them because we can talk about them at the same time. It highlights this issue of minimizing the 0-1 loss. But then there are other classical interpretations, a modeling-based interpretation for logistic regression, and for SVMs, there's this idea of separating hyperplanes and support vectors, which is very important just for your own edification to understand those motivations. So we'll return to that in the next video.